So this afternoon, we're going to continue our session in reference to drives. We're concentrating now on slide 32. Everybody should be there, hopefully. Right? Everyone there? So in here we have the different types of technology available. Depends on your needs. RAID has its different flavors and colors. You have your RAID 0, your RAID 1, your 5, your 0+1, your 1+0. There is, I believe, 6, but for the necessary of A+, those are the ones that we are concentrating and working with. The main purpose of this usually is either for data redundancies or performance improvement or both, depending on, again, what is it that you need from the server itself. RAID is usually used on servers. It's not something that you would go and waste your money on your computer unless if you have the money to go and do this for no apparent reason. So basically what it does is the data is distributed across all drives in one of these several ways. You have your RAID 0, your RAID 1, 5, 0+1, and 1+0. Basically, we'll get into those details real soon. Next slide is 33, your RAID 0. Your RAID 0 sets without fault tolerance. It just requires at least 2 drives, doesn't provide redundancy if one of the fails at all fails. This is more for striping purposes and performance on those servers where applications maybe doesn't really require a copy, but more in speed, more interested in speed and how it's using it. If you'll notice there, striping, why? Because disk 1 will do block 1, disk 2 is doing 2, then 3, 4, just keeps on using the drives throughout the process to ensure that the speed is at optimal. Horrible part about this obviously is that you have no contingency at all. RAID 0 doesn't give you any fault tolerance. RAID 1, now here there's mirror or duplexing is what it's called, requires at least 2 drives and they must be from there always even, all right? You always lose half storage to be able to duplicate the information if one of the drives fail. So if you'll notice here, 1 through 4, 1 through 4. Everybody gets the same exact information compared to RAID 0. Each one is holding different eggs in the basket and there is no redundancy. Question in reference to RAID 0 or RAID 1. Can you explain to me the main difference between 1 and 0, Alexa?
1 has chipset without fault, and the other one is, oh, well, 1 requires.
Yeah. They both require 2 drives, but 1 requires an even amount, right? That's a major difference, right? They both require at least 2 drives, but one of them always requires an even amount of drives for to be able to mirror or duplex the information. You always lose half of your space. So if you have 2 1 gig drives, you only have 1 gig of space because one's utilized totally for just mirroring or copying the exact amount of data. Thank you, Alexa. Going to slide 34. Here we get a little bit more complex. RAID 5 is stripe set with distributed on a parity bit. Everyone remember the parity bit? Right? The most common RAID implementations is because it's the fastest way to provide redundancy. I don't require all that space like in mirroring. It requires at least 3 drives to be able to complete the process. And obviously distributes the data and a parity evenly across. So if as we can see, there's 5 disks here, and you'll notice that it uses bit on the file A. Let's pretend this is A here. It creates 4 bits, right? And then right here, or what we call a nibble, right? And then it has this parity bit for the nibble. So if I lose this drive, right? It's very easy to figure out with these 3. If I have a parity bit, I know if I'm missing either a 0 or a 1 here. Do we all agree? So Jordan, how would I know if this was 1 0 1 0 0? How would I know if I lose this drive, what was its number? What's the major thing that I'm gonna, as a drive, how would I notice? What's the major thing that I'm looking for with this parity bit that's helping me? It should be helping me to do what? What does the parity bit do for me exactly? It should be doing only one thing.
It gives an extra bit of information to make it all uniform.
Even Steven, right? So when I add out of those 1, 2, A1, A2, A3, A4, out of that, I should have either an even number or an odd number. And my parity bit is either going to make it even or let it stay even by either putting a 1 on an odd number or a 0 to keep it even to an even number. So if I lose one of these drives, that parity bit is going to let the RAID controller know what is missing. Is it a 0 or a 1? So that if something happens to that drive on my own, based on that parity bit, I could continue to work as if you were with all 5 drives. The user and or server, the only thing that's going to happen, obviously, is the performance is going to be a little bit hurt until it tries to recover itself. We don't want to leave it all out there like that because it's going to start using only 4. So it'll start trying to reconstruct its information based on the parity bit. When you put the new drive back in and it formats itself, then it can reconstruct all the files and finish the process. Any questions? So we need at least 3 disks. The more the better, because obviously if something happens to a disk while that's happening and while it's replicating and fixing itself, usually they tell the technicians if the drive is going to take too long, make sure you probably put a RAID, set it to 4, let it start reconstructing itself so it's not any more risk can happen. It's going to take a while so it can start creating those and creating itself to being used to 4, and then eventually add the 5th drive back and let it reconstruct itself, make it the RAID reconstruct itself based on the 5 drives. Those are things that we would learn, but the concept we need to learn is the amount of failure. I can only lose 1 drive at a time until I reconstruct my whole RAID array. If I lose 2 drives, I got too much information missing. There's no way the computer is going to be able to figure it out because now I'm losing 2 parity bits. There's no way it's going to be able to recover. It can only recover from 1 failure. Any questions, doubts? You notice also it stripes the parity bit. Doesn't leave all the parity bits in 1 drive. The parity bit is pretty much striped across to make sure all your eggs are not in 1 basket. Okay, let's continue on to slide 35. We have the RAID 0 plus 1 or RAID 1 plus 0. It all depends on how you want to set it up, but they ultimately do the same thing. The variance is here on the RAID 1 plus 0. Your RAID 0 is basically striping the information across two RAID 1s. RAID 1s we learned were mirrors. So as you can see here on the left side, I have 4 drives who are acting as 2 drives. Lack of a better way of explaining it. The RAID 0 is making sure that the information is being striped. So I have A1 going in here and A2 going in here. But then my RAID 1 in the inside is making sure that the information is mirrored across the 2 disks. So this RAID section here has a mirror, A1, A1, A3, A3, A5, A5, A7, A7. Same thing on the other side. Now that it's striped it, A2 went in here, and then make sure that it makes an exact same copy within those 2 disks. So looking at this, obviously, this here gives me a little bit higher redundancy, right? Technically, I can have, if I'm lucky enough, I can have 2 disks that go down, right? 1 per each array, right? Because if one of these disks goes down and one of these disks go down, I'm okay. But if 2 of these disks go down on this array, I am completely down. Questions? Same here. The variance in this one is that in the RAID 1, or what they would like to consider RAID 0 plus 1, it has the RAID 1 on the outside. That means the mirror is going on the outside, thinking of this array, and then the RAID 0 is in the inside. So these 2 drives will be striping the information. There's no duplication. And then this side over here, the same thing, the exact same copy that's over here, but it will be striping. Once again, I can have half of the failure as long as it's not the 2 disks that have the exact same information. Questions? Come on, guys. I don't think RAID is that easy. If RAID was that easy.
I'm confused on which one is the RAID 10, like it says there.
RAID 10 is the guy on the left. It has
Is it 0 plus 1 or the 1 plus
1
0?
plus 0. 1 plus 0. So then the RAID 1 would be the RAID 0 plus 1.
Okay.
So you could always think about that. You look at it in the inside here. So that's your 1 and then your 0. Same thing here. Your 0 and then your 1. What's it doing first? Here it's mirroring the information and then striping it across, versus here it's striping and mirroring across. At least that's the way I'm able to memorize it, of how they write it. Doubts? So it's just using the 2 technology to accomplish the 2 jobs. We want to be able to have the performance of striping while at the same time having the actual mirroring. It's not the same as RAID 5. RAID 5 uses a parity bit. I'm still losing half my space. Do we all agree? On RAID 0 plus 1, 1 plus 0, just like in my other mirror, I still lose half my space. Only variance is that I get up to 2 failures. So here's a little chart to help us on page 36 of this presentation. RAID 0, minimum 2 drives. Doesn't matter, you can't fail any of them. That basically is only striping. So it's just for performance, so it can write it across the 2 drives, right? RAID 1 is minimum, again, of 2 drives. Has only 1 fault failure. We are mirroring there, so it's copying the identical to the other drive. So only 1 drive can die without impacting. RAID 5 requires a minimum of 3. Another thing to remember on RAID 1, we need a minimum of 2, and it always has to be in pairs. It has to grow in pairs. I can't put an odd number there like I can in RAID 0. RAID 5, we said, was a minimum of 3, and we can only fail 1 using the parity bit. RAID 0 plus 1, minimum of 4 drives for both 0 plus 1 and 10 to be able to mimic, and it supports up to 2 as long as it's not the exact same 2 with the information. Any questions on this chart? Teresa, I think you're about to kill me. Your eyes tell me you're about to hunt me down.
No, I get it.
Okay. No questions? Come on, guys. Really? RAID is this simple? Okay. All right, hardware versus software RAID. Software RAIDs means the operating system is in charge of all RAID functions. You don't have a controller or a piece of the motherboard that actually does the job. It works for small RAID solutions, but tends to obviously overwork the OS. We shouldn't be doing this with big servers. We should be having, hopefully, a hardware array that does this for us. It actually can control the RAID controller and make the operating system make it look like it's all one disk. Don't even notice what's going on. The Windows server obviously has a disk management program that allows you to configure 0, 1, and 5, and it works both on SATA and PATA. Windows Vista can only do 0. I don't think anybody's doing that anymore. Windows 7 and 8 allows you to do RAID 0 and 1. Again, that would be software. The hardware RAID centers is actually a controller itself that handles the RAID functions. This memory control has chips on their own and a BIOS ROM that you'll be able to configure. It allows also for hot swappable drives. These are more sophisticated than the operating systems themselves. It's used when performance is a priority since it provides speed along with data redundancy. Questions? The hardware versus software.
Got a quick question.
Mm-hmm.
Is it still possible to do a hot swap with a software-based controller?
Who?
Hotspot. Is it still possible on a software controller?
On a software controller, I believe you're supposed to stop the RAID before you pull it out. You have to stop the disk from being on the RAID, I believe. I'm not aware of too many of the software ones being hot swappable.
Okay, so
And now there is a server versions where the server itself, again, has the controller and it can handle it. So once again, the operating system has nothing to do with it, and I can hot swap. And that would be usually the hardware ones. Those don't care. I can pull it out and put a brand new drive, and it'll do everything. It'll recreate the RAID and everything.
got it. So
Hello,
software.
hello, Diego.
On the software.
Hey, how you doing?
All right, man. Sorry I interrupted. So let me come. I have a call right now at 1:30. So let me prepare, and I'll see you guys in a little bit as soon as I'm done with that.
Okay. Thank you for letting us know.
Yeah, I'll be back.
Okay. Okay. Was there another question, Lázaro?
I'm just saying that it's safe to say that hardware RAID should always have hot swapping, and then software depends on the software.
Yeah, I haven't seen too many softwares. Once again, I haven't, because usually when we have the hot swappable, they all had a RAID controller in it. I doubt there's many software that allows hot swappable. I don't think there's many. I haven't seen them. At least the operating systems that I've seen. I've never seen it that way. Usually, if it's hard, you have a RAID controller on the motherboard. They're usually on these blade servers. They're very skinny servers that go on a rack, and then you could just put in and out drives like if it was nothing, without having to turn off. Hot swappable means I don't have to turn off the computer. Just for those that maybe were unsure what we mean by that. Thank you for the question. Let's proceed to 38 if there's no other question on 37. Factors to consider when purchasing a hard drive. Obviously, the capacity of the drive. The more gigabytes and terabytes, the higher the price. The magnetic drives have larger capacity and money than solid state drives because you'll be getting more bang for the buck. Obviously, they have more performance issues because they run slower. Most of them are 7,200 RPMs is usually the highest they can run. Those are the regular hard drive compared to the solid state drives don't have any moving parts. Interface standards for motherboards are usually SATA. Nowadays is SATA 2 or SATA 3. The external ones are eSATA, FireWire, or super speed high USB, and cache or buffer size. These magnetic hard drives have a buffer memory that's on that board that we said, which improves overall the performance. And depending on the hard drive, it can have between 2 megabytes to 120 megabytes of buffer size and cache to obviously help the overall performance of whatever you're working on the moment. Any questions on slide 38? Hello, 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 hello. Really? Guys are geniuses. Come on, guys. Killing me softly. I know you can do it. You got a question. Somebody has it. Nobody? All right. Let's continue to 39. You can read this for me, Jordan.
Steps to install the drive. Number 1, shut down the computer and unplug it. Then press the power button for 3 seconds to drain residual power. Remove the computer case cover. 2, decide which bay will hold the drive. Examine the locations for the drive bays and the length of the data cables and power cords. 3, for a stationary bay, slide the drive in the bay and using a screwdriver, secure one side of the drive with 1 or 2 screws. Another option is a sliding tab that is used to secure the drive. 4, decide which SATA or IDE connectors on the board to use. 5, connect the 15-pin SATA power connector or 4-pin Molex power connector from the power supply to the drive. 6, check all your connections, power up the system, and verify.
Thank you. Pretty much self-explanatory, all the steps here. Does anybody have questions overall? No? Come a little bit familiar anyways, the steps of shutting down, making sure everything is disconnected. Here's a picture of the drive bays, depending on, some of them have a little clip here. As you can see, this one has a screw where you need a screwdriver, but this one will be just a little latch where you slide and it releases it. So a lot of the times these things have a little track on the side that you screw the track and it has a little doohickey that locks on in place. So no need for a screwdriver, just hit the little latch and it'll come out. Our usual troubleshooting, going to slide 41 now, troubleshooting hard drives. And let's see, my little application here. Who do you pick next? Justin. Thank you, App. Can you help me with this slide 41?
Troubleshooting hard drives. Slow performance. It is the result of the use, writing, and deleting data of the magnetic hard drive solution. Run a defragmentation tool. Problems during boot, if the UEFI or BIOS cannot find a hard drive at post, it displays an error message. The solution for that would be either 1, remove and reattach all drive cables. 2, inspect the drive for damage, such as bent pins. 3, determine if the magnetic hard drive is spinning by listening to it. 4, checking the cables for frayed edges or other damage. 5, checking the UEFI BIOS setup for errors in the hard drive configuration. And 6, trying to boot from another bootable media.
Thank you. Any questions on the slow performance? Do you guys understand why it will be writing and deleting data all of a sudden? Christina.
Can you explain that part?
So if these drives start failing, sometimes sectors are bad or start going bad. So information starts deleting. The magnetic drive is trying to magnetically write information in there. So one of the things we would like to do is to run a defragmentation tool, which basically at the same time checks the hard drive. So it organizes it. What we need to understand is that these drives are spinning so fast. And a lot of the times, this is in reference to Windows that they're talking about, because Linux doesn't have this problem with the hard drives. It's amazing what they can do with their operating system. But somehow, it's the wild, wild west when it comes to writing information on these spinning hard drives for Windows. You could just imagine, since it's spinning so fast, they've decided to let it write wherever it wants the information. And what it does, it keeps tracks of that information on a table. It says file 1 is on spot 32, and then there's a little tab next to it that says where is the next part. So then on that table of contents, to lack of a better thing, you can pretend it's an Excel sheet. The first table says what's the file, and it also checks the actual state of that sector. So it marks if it's good or bad, so it doesn't use it again. All this happens when you're doing these defragmenting tools. And what he does, he puts Humpty Dumpty back again. Everything's written everywhere. But what he does now is, since he has this table, he can look at file A. You're everywhere around here. Now, I'm going to move you to this side, and it's going to be in order so that when I read, I can just read it all at once in one pass. Compared to if I leave it as it is and I don't defrag my actual hard drive, it'll continuously start just using only empty spaces that are out there, and it starts getting filled up, your hard drive, and the more that it gets filled up, the more it's got to run around looking for empty spaces to keep on running, and the more it's got to go back. When it's got to go back to that file, the more it's got to jump everywhere. So the best thing is defrag. They have that tool within Windows. You go to your hard drive, you defrag your drive, and then he puts everything back and tries to use your space, obviously, better. It's going to get bad again, because after you do that defrag, when you start writing all that new information that's coming out, it actually then starts doing the exact same thing. Questions? Doubts?
I have a quick question. Does defragging still matters for solid state drives?
That's a great question. This is only for the spinning hard drive. Doesn't happen with SSD. Solid state drives uses memory, so it allocates it in order.
Roger.
That's another reason why performance is much faster with the solid state drives. Any other questions on this slide? Are we sure? Are we there yet? 2, 1, a la Juan. A la
Quiz
two.
time.
Mm-hmm. Hello? Yes? There was a question?
Saying it's quiz time on next page.
Yeah. Let's see here. Hold on a second. Next slide. So, number 1, Jordan, if you can help us here answer this. How is data stored magnetic tape? How is it stored?
The parallel?
Okay, we got 1 vote for parallel. Everybody agree?
See, no, sequentially.
Yeah, I think it's C.
Okay.
Because if it was parallel, it'd be pattern.
Okay.
Hmm.
All right. So we got a 1 vote for C, or sorry, 2 votes for C, 1 vote for parallel, which is A. Any other thing, maybe something else besides A or C? So if we look at the tape, if we remember, the tape is coming through a little spinning wheel, right? You could pretend it's a cassette tape, and then the tape goes like that. at one point there is a head, a magnetic head where it touches the tape. And as Teresa and Mohammed alluded to, the only way it writes it is sequentially. Keeps on reading the tape, pushing the tape through and writing the information sequentially, and then you just go and store the hard drive, or sorry, the tape wherever you like. But it is in sequence. Thank you. Number 2. Which of the following best describes RAID 5? RAID 5. Justin.
The answer would be it requires 3 or more drives and uses parity checking.
Okay. Daniel, can you explain to me what RAID 5 does with this parity checking? What does that mean exactly? Parity checking on RAID 5? Daniel? You're on mute.
Uh,
There we go.
oh. Parity checking to see like the performance.
Okay. Everyone agree that parity checking is check the performance of the drive? Anyone disagree? What do they believe if it's not for
What's the
performance?
question again?
We're on question number 2, and I asked a follow-up question in reference to RAID 5. We know that it requires 3, excuse me, 3 or more drives, and it accomplishes it. We're using parity checking only. So, do we believe parity checking is for performance on the drive?
Oh,
Yes.
no.
So it's
It's for
No?
checking the data redundancy.
Okay. So we
Checks
have
for
yes,
errors.
no. Anybody else want to chime in? So we got 2 that say yes, is
Yeah.
RAID 5 is for performance.
It checks for errors like the 0, 1, 1 thing that which is right and which is wrong. I just hardly
When does the
remember that.
parity, how does a parity, and when and where does a parity bit get used?
It's an extra bit. This way you can check the data, see if it's missing a 0 or 1.
Correct. Would that actually help me go faster?
Yes.
yes.
I
It would
think so.
actually
Go
help me
slower.
go faster?
Go slower.
Just keep your
Slow?
data
It'll be,
very secure.
can we agree that it's slower than striping, which is RAID 0, but faster than mirror, which is an identical copy? Can we agree to that level?
Yes.
Right? Because in a mirror, it creates a whole identical copy. In striping, it doesn't copy anything. It is the fastest, and it just keeps on writing as fast as possible. This one here has striping, plus it has a 1 extra bit that it's going to be writing. 1 extra bit. So 1 extra 0 or 1 that it will write. It's not going to make a copy. No copy is being made. All it's doing is creating it an extra 0 or 1 to be able to identify if there's something missing from one of these drives when they go down, or when I'm reading these drives, I compare the parity bit to see what's wrong. Question or doubts? So parity checking is basically that, to see if whatever the 4 parts were, or the nibble that I'm looking at in this example, from there, that parity bit should be able to then tell me which one is wrong and be able to recreate it. I'm missing a 0 or 1 in this file. Questions, doubts?
So
Okay.
I have a question. So if one of the drives fails,
Mhm.
it has the other drives has what that drive should have in it.
No, I'll show you. Great question, though. I do enjoy that question. Thank you very much. Exactly why I was worried in reference to this. So we have, you guys can see my whiteboard?
Yes.
Yeah.
Yes.
Drawing. Oh my God, you got a Picasso going on here. Thank you, Diego.
Mm.
All right.
Nice.
So here is my file, right? Then in here, there's going to be an extra bit who's going to keep track if this was even or not. That's just a bit. If you notice, I don't have the 1, I don't have the 0, I don't have a 1 and a 0 stored in this little thing. All I'm going to do is make sure that it is going to stay either even or odd. So if I come and I look at this file again, I have a parity bit of 1, there I know that there's something wrong with this file. And it's able to reconstruct and know which one is supposed to be a 1 and which one is supposed to be a 0. So
I'm
something
asking,
happens.
where is that stored? Where is that stored?
It's just a parity bit, and the drives and the RAID itself is able to keep track of everything and check to reconstruct everything. The RAID controller or the RAID on the operating system is able to tell where that was supposed to be. The parity bit is the one that marks it to make sure that you're aware of if that section of the nibble was even or odd before it tries to fix it. Just like your error checking memory, right? You guys remember your error checking memory? We had the parity one and the ECC. You guys remember in the memories? We had a parity memory, right? Plus ECC. So you could pretend the first part of RAID 5 is the parity and the second part of it is the ECC where it knows to correct it based on that parity bit. Using the same idea and concept, that's what RAID 5 is doing. Is using a parity bit to be able to reconstruct everything. Questions? Doubts? They're all 1s and 0s at that point. And based on that, it knows where to put a 1 or a 0. That's what the parity bit does. Okay, next question. Number 3, Pablo.
Wait, am I muted? Okay.
Question number 3.
Which of the following is not true about hard drives? Let's see. A, the 3.5 size typically use desktop. B, solid state drive. It's not true. Okay. Solid state drive, and then tracks on the hard disk. I would say B. Solid state
That's
drive.
not true. That's not true. Solid state drives have no moving parts. It's not true of them. Everyone agree? Okay.
No.
They don't have
true.
moving parts.
I'm confusing something else.
So which one
It's
you guys think? Anybody want to chime in maybe and vote?
C.
C.
It's C. I think it's C.
I got several people, including DeAndre, telling me C. Everyone agrees? C. Solid state drives are less expensive than magnetic hard drives. That is absolutely false. That's not true. We learned that obviously solid state drives are much more expensive per the gigabyte. The old hard drives with the mechanical parts are much cheaper. I can get a much bigger hard drive per dollar. Otherwise, yes, they are a typical size 3.5 in desktops. SSDs do not have any moving parts, and tracks on the hard disk are divided into sectors, is what we learned in the drawing at the beginning. Next one, Carlos, number 4.
You want me to read the question?
Yes, please.
Okay. Which interface is not typically used for an internal tape drive? I think it's FireWire.
Everyone agree?
I
FireWire?
agree.
Yeah, Firewire was that extent of Firewire. Usually the Game Boys have it, and I think there's newer Firewire. There's a Thunderbolt, whatever they call it nowadays. It's usually an external cable, correct? And not used with tape drives. Number five. DeAndre, you can help us read number 5, the question, and if possible, answer it.
Which of the following is true about hardware RAID?
Yeah, hardware RAID. So not the OS, but the actual hardware one. Anybody want to take a wild guess?
Wait, hold on.
Okay.
I think. Oh,
I think it's
Let's
D.
give DeAndre a second here. I'm sorry, which one?
Is it D?
That is correct. If they have their own BIOS, as I stated, that's the feature that helps us also with that hot swappable stuff, where the BIOS is capable of allowing us to do this. They have their own controller. These things are very expensive, obviously, for the features that it brings compared to the OS doing it for you. Because now the OS is mimicking what the hardware is doing. Any questions on questions 1 through 5? Yes, no, maybe so. All right. This pretty much ends up our session here. I'm stopping recording if there's no questions on this.